All right, so last time we talked about Newton's first law. Go ahead and move into Newton's second law. And we've been talking about forces, but with Newton's first law, it's specific to when forces always cancel each other out. There's either no movement or uniform movement. Newton's second law deals with what happens when these forces are actually unbalanced. So again, a force is essentially just a push or a pull. Um, the nature of this force could come from anything: gravity, an electromagnetic force, nuclear force. There's lots that we'll talk about throughout the rest of the course. So knowing what a force is and how they work is really crucial right now. So the idea of unbalanced forces acting on an object, uh, since they're unbalanced, we can add them all up, and some parts will cancel, some may not. The whole point of adding them up is to actually just represent everything as one single force, the net force. Okay, now if we add all the forces up and find a net force and it's not zero, that's definitely not Newton's first law. Okay, so anytime you add those forces up and they don't sum to zero, we're looking at Newton's second law. So the whole idea is essentially if you want to increase the acceleration of an object or give an object an acceleration. Now that could be if you're in a car and you've got some velocity to the right and you want to slow down. Maybe you're coming to a stoplight and you want your velocity vector or your speed to become smaller. You need to apply an acceleration opposite your direction of travel. Or if you want to speed up, you need to apply it in the direction of travel. So anytime you want to change the acceleration, what you want to do is apply a force. Because the source of the acceleration is going to be from a force. Okay, so anytime you're causing an acceleration, you're literally just unbalancing forces. You're causing the net force to act on it. Okay, now we say that an object's acceleration is directly proportional to the net force acting on it. Okay, so we have an acceleration, it's directly proportional to the net force acting on it. And we say that we can say that in a shorthand. The little squiggly here, it's called a tilde. Basically, this just means acceleration is directly proportional to net force. Okay, so if we look at this example over here on the right, so we have some force acting on this brick and it's causing an acceleration. Okay, well, if we double the force, you'll notice there's two hands on there. Well, that means we have to double the acceleration. So in shorthand, we have acceleration is proportional to net force. But if we double one, so 2a is directly proportional to double the net force. We could even, if we wanted to triple the acceleration, that means we'd have to triple the net force. So you get the idea. Okay, now let's talk about some of the things that actually start causing unbalanced forces here. So we have friction, which is basically when two surfaces slide over one another, a force of friction acts. And you can feel that in your hands just from rubbing them together. They get warm, and that's from friction acting. So when a force of friction is applied to an object, it reduces the net force and acceleration. Okay, so here's a way we can actually reduce that net force and in turn reduce the acceleration on the object. So, if you push something across ice, it'll really take off and accelerate. But if you push something across carpet, it's going to go slower. You're going to have to apply more force. And that's literally just the difference in how much friction you're getting. But friction really is just caused by the interactions between those two surfaces. You can see here in the picture that is essentially just the surface roughness, even at the microscopic level. those really rough surfaces interacting with each other. That's what's going to cause your friction. So something to remember, and this is important when you're setting up problems in your problem sets, the direction of the friction is always in the direction that opposes motion. Okay, so in this picture here, we've got this block sliding down the ramp. We know it's going to slide down. That's just common sense. So whatever the direction of your motion is, friction's always going to be in the opposite. So just keep that in mind. Sometimes these problems do get a little complicated. So sometimes it's good to just take a step back and think about, okay, well, which way should friction point? You can ignore the math and just draw a picture, and usually it's pretty telling. So there's two different types of friction that you need to think about. You'll notice over here I have a little F sub K. This K stands for kinetic friction. And that's a friction on something that's already moving. Static friction is actually when something is not moving and you've got friction holding it in place. So I could do a quick demo, like my phone is on top of the book, and even though this is tilted into a ramp, my phone's not going anywhere. So this is static friction, static friction, static friction, static friction. And as soon as you hit that tipping point, it changes to kinetic friction. So it's static all the way up to right there. Then it becomes kinetic friction. So that's what I mean by static friction is variable, and then kinetic friction is constant. Because as I increase the incline, I have to add more and more static friction. Well, the system has to add more and more static friction to keep the phone there. But once the phone starts sliding, you just get the same amount of friction all the way down the ramp. And I'll show you a plot of that here in just a little bit. Oh, I guess I'll show you this right now. So let's look at this example. So let's consider a book sitting on a table and there's no horizontal forces. Okay, so you can look at the picture, there's nothing in the X direction. So if we sum up the forces in the X direction, we get 0. And now if we think about the weight and the normal force of the book, we know that the normal force points up, the weight's going to be negative, right? It's pointing down. We can define our positive and negative direction any way we want to, as long as we keep it the same throughout the problem. So I'm going to call this positive Y direction. This direction can be positive X. Positive X doesn't matter right now because we don't have any forces in the X direction. But we do know that N is up, our weight is down, so it's negative. Those two have to equal 0. This is Newton's first law. Because the book is not moving up or down, those two things have to cancel each other out. But what if I apply a tiny push to the right of this book? Okay, so I'm going to come in here and I'm going to push this book to the right. And that's just going to be a tiny force vector. Now, I can take this book, this big book, and I can push just a little bit, and it's not sliding across my hand, right? If I push it really hard, it will. But just applying a little push is not going to do anything. That's because there's friction between this book and my hand. This friction is fighting my little tiny baby push right here. So you'll notice this tiny vector is being canceled out by this force vector opposing it. Everything still equals 0 in the X direction. Nothing's changed. Okay, well, look at what happens here. So I can give it a little more push. Okay, I can increase my push and make my push less tiny. So you'll notice, let me erase if I can. There we go. So you'll notice that the two vectors here, My push vector gets a little bit longer because I'm pushing a little bit harder. And look at what happens here. My static friction vector also gets a little bit longer in the opposite direction because these forces still cancel out. So the only way to do that, if I increase the force pushing, static friction has to increase itself to compensate. So anytime you're trying to push something, and if you start with a gentle push and push harder and harder, you're actually changing the friction vector. You're actually increasing it in the opposite direction. Now, obviously, I can push on this hard enough to make this book start moving. And as soon as that happens, that means the static friction was overcome. So I broke static friction, but obviously there you can still feel resistance when you're pushing something across carpet, even though it is moving. So in that situation, I've overcome static friction, but there's still kinetic friction. But look at the difference here. If I were to sum up these forces, they're unbalanced. They don't cancel each other out anymore. This push is a big vector. This kinetic friction, not a very big vector. It's still fighting the push, but it's not a strong vector in the opposite direction anymore. Let's see. So this should be, there we go. This should be FK. My bad. So what you see is the push minus the force of friction. That does not equal zero, right? Because those forces are unbalanced. Let's talk about friction just a little bit more. So static friction will increase until it hits a maximum value. We just saw that. So after this point, an object will begin moving and only be opposed by kinetic friction. So once you actually get this thing moving, the force of friction does not depend on speed. So that means the faster you push is not going to increase friction. It's going to be the same amount no matter what the speed is. And what's really interesting is friction does not depend on the area of contact. So my hands are both similar material, so the force of friction here between my two fingers will be the same as if I use my whole hand. So surface area doesn't matter. So let's look at a plot. If we think about this plot and how it applies to friction. So let's think about, so this is going to be my push, like from the previous example. So I'm pushing, I'm increasing my push, I'm pushing stronger and stronger. And then also pushing back on me is my frictional force. So yeah, we'll label this here. So that's going to be my resistive force. So just like in the previous problem, if I start increasing, maybe I go here. If I apply this much, we'll call this P1 for my first push. If I apply this much of a push, I get this much static friction, right? So you've got some amount opposing me. The amounts are the same. So let me draw that in. So whatever this amount is, it's got to be the same as this amount. Okay? Those two things have to equal each other. I'll call this is my first push. Now I could increase my push, maybe come over this much. Okay, so I'm going to come over, here's my second push. Here's the amount of my second push. Okay, that's going to correspond to some amount of friction. So that's my second one. But again, you can see that the harder I push from P1 to P2, my push is increasing and the friction opposing me is also increasing. But look at what happens here. I can give it a really, really hard push. So maybe I'm over here on my applied force scale. I'm over here at P3. So I'm pushing it this hard. But the friction force that's opposing me is now kinetic friction, right? I broke over this point. So this is when that's when your friction, your static friction, breaks when the thing starts moving, and then you switch to kinetic friction. At that point, you see you get this increase in static friction. All of a sudden, it becomes kinetic friction. So everything over here is static friction. Everything over here is kinetic friction. So you'll see finally the push is going to be greater than that kinetic friction that's opposing it. So friction is not just for solids brushing against each other. Friction also occurs in liquids and gases too. So you could think about like a meteor coming in, you see it like heat up and burn up in the atmosphere. That is from the friction in the atmosphere. So fluid friction occurs as an object has to push that fluid out of the way and the fluid sort of going over the surface. You can see that here. You can see as the atmosphere is going over the car. I think in this case, this car model is actually like in a water tank, but it turns out that flow in water and the atmosphere actually works the same way. So you can see that this car has to exert some forces, or there's forces exerted on the car to move this stuff out of the way. So that's where the source of fluid friction comes from. What's really interesting is a common form of fluid friction that you deal with on a daily basis is air resistance. And air resistance, actually, it depends on speed. So regular friction does not. Air resistance and fluid friction does depend on speed. So this is important to note that fluid friction does increase with speed since the object moves air out of the way. So it's how fast it has to move air out of the way is sort of what drives that. And if you're interested, I have included an article here about why air friction affects your gas mileage, if you want to read a little bit more on that. Okay, so we've talked about forces, we've talked about acceleration, and we've talked about some of the forces that change acceleration, which is friction. So now let's talk about the other thing that will affect your acceleration that is related to Newton's law, or Newton's second law. So mass and weight. The acceleration imparted to an object depends not only on the net force, but also on the inertia of the object. So remember, acceleration is, to write it this way. There we go. So remember that acceleration and net force are directly proportional. You increase one, the other one has to increase. But there's something else that affects acceleration, and that is inertia. So how much inertia an object has, that really just depends on the amount of matter in the object. So the more matter, the more stuff, the more inertia. So in speaking of how much of a thing there is, we usually talk about that in terms of mass. So more mass equals more inertia. So inertia goes up if mass goes up, or if there's a lot of mass, there's a lot of inertia. So let's think about what the difference between mass and weight are. So mass is the quantity of matter in an object. I mean, it's essentially a fundamental measurement. Like if you talk about a bowling ball, the mass of the bowling ball would literally be how much of the bowling ball is there in front of you. Or when you talk about a person's mass, that is how much of a person is there in front of you. It's also the measure of that object's inertia. And then, of course, inertia really is just sort of like an object's laziness to change. So obviously, if we had a 4-year-old sitting in my office chair and you pushed it, well, the 4-year-old does not have a lot of inertia. They don't have a lot of mass. So if you push them, they'll go flying across my office. If you try to push me, I have lots of mass. There's more of me. So I'm not going to travel as far and as fast. So the whole idea here is that mass, this does not change. For any object, mass is always the same. Okay, now weight can change. Weight's different. So usually, and I'll talk about why I say usually here in a second, the force upon an object due to gravity is what causes your weight. And we've talked about that. We always draw the weight vector down. And that's always from gravity, from the mass of the planet pulling down. Now, there is a way that you can have a weight without being on a planet, and that's where this stuff over here on the right comes in. So this guy here is Wernher von Braun. He's actually a former Nazi that came over in World War II and wound up running one of the NASA centers. He was a wonderful rocket scientist, and he's very famous. He's got an interesting story. Got a link here if you're interested in reading more about him. But something he designed was a space station that's shaped like a donut, like this. So the whole idea was you could simulate gravity by spinning this. And if you think about it, if this spins, it'll sort of sling everyone to the outside. And then people will be walking with their heads facing into the ring this way. So all of your living quarters would be turned sideways on the inside of this ring. And if it's spinning, you would feel like you're on a planet. You would feel like you're on Earth. You could spin it such that you could make the gravity just like Earth. So the whole idea is that you don't need, that's just another person, their heads would be facing in, walking around the inside band of this thing. But the whole idea is that if you spin this, you can still simulate weight, right? Weight's just a simulation. You can simulate that without actually being on the planet. Okay, now, if we think about a 1 kilogram brick, okay, now this is a mass, a 1 kilogram brick. Kilogram part doesn't change. If you take that 1 kilogram brick to the moon, it's still a 1 kilogram brick. But if it weighs 10 newtons here on Earth, okay, now this is a weight. If it weighs 10 newtons here on Earth, you take that brick to the moon, it's only going to weigh about 1.67 newtons. That's because the gravity on Earth and the gravity on the moon are very different. Which means that essentially, this will sum this up, your mass will always be constant anywhere in the universe, but your weight depends on where you're at. Your weight could be whatever. It's totally dependent on the planet you're on or the ring spaceship that you're flying in. Now, here's a new type of relationship we need to discuss. So we say that for a given force, the acceleration produced is inversely proportional to the mass. Okay? Now, inversely proportional is a little bit harder. So that is, acceleration is inversely proportional to the mass, or yeah, that's why we have the 1 over. Okay, so the 1 over is going to be inversely proportional. I'll abbreviate. So basically, if acceleration increases, mass decreases, or if mass increases, acceleration decreases. So in the previous example, we had acceleration increasing, force increasing, acceleration increasing, they flip together. These two are opposite. So whatever, when it comes to mass and acceleration, whatever one does, the other one does not. So if we look at this image here, you've got force from the hand, and we have a little bit of mass, right? One brick of mass m. Now, if we add two bricks, we suddenly have 2m. Okay, well, our mass is increasing, which means our force has to go down. This becomes 1/2 of the force. If we increase to 3 bricks, so 3 times the mass, we get 1/3 the force. So that's the whole idea. And you can see that here in the math. If you have a fraction 1/10, that's a pretty big fraction. If we increase the denominator, so 1/1000, small fraction, right? We had to crank up the number in the denominator. We made the number larger, but because it's in the denominator, we made the overall value smaller, right? 1/10 is pretty big compared to 1/1000. So this brings us to Newton's second law of motion. So Newton was the first to discover the relationship among these 3 basic principles: acceleration, force, and mass. And Newton's second law states that the acceleration of an object is directly proportional to the net force acting on the object it's in the direction of the net force, so the acceleration is in the direction of the net force, and it's inversely proportional to the mass of the object. Okay, so we literally just smashed all these things together, and look at what we have. If we use the right units, instead of just writing this as a proportion, we can write it as an equation. So it turns out we can state Newton's second law in an equation. So this is Newton's second law. Acceleration equals net force over mass. Now, of course, we can write that in mathematical shorthand. So our net force, we just label as the sum of the forces, right? Sigma F. And mass, we always just represent as just m. And then acceleration is always a. Now, notice some of these values are vectors. That's why I have a little vector head on it. So acceleration, that has a magnitude and a direction. We can talk about how the speed is changing and in what direction. Is it speeding up? Direction's pointing forward, or the direction's forward, or are we slowing down? Our acceleration vector is pointing behind us to make us slow down. Okay, so our mass is going to be measured in kilograms. Remember, this is not weight, it is mass. It's how much of the object there is. The net force is going to be in newtons. So we can write newtons as the units of force, but something to remember is that the unit of newtons, that's actually just a simple way to write kilogram meter per second squared. That's also newtons. The combination of all of these units together is a newton. So we just write n instead of writing all those units. And of course, our acceleration is going to be measured in meters per second squared. So the acceleration of an object is always in the direction of the net force. Now remember, I said that the acceleration could point opposite of our motion. That's totally fine. But that's because the net forces are pointing behind us to slow us down. So acceleration, net force, they always point in the same direction, but they don't have to point in the direction we're traveling. Okay, so we could be maybe traveling this way, but maybe our velocity is slowing down, so we have a negative change in our velocity. Okay, so remember, delta means a change. That change is negative, so we're slowing down. Well, that means the net force, it's got to be pointing the opposite direction that we're traveling. That also means our acceleration's got to be pointing in the opposite direction. So applied in the direction, same direction, we increase our speed. Applied in the opposite direction, we decrease our speed. If we apply forces, maybe we're traveling this way. If we start doing crazy things and start applying forces off to the side, that changes our direction. That's literally how we turn. Okay, so we can change our speed and our direction if the summed forces actually point, if that net force points in a different direction. Okay, this is just a side quest here. So Newton's second law can be rearranged. So instead of having A equals sum of F over M, we can literally just multiply the M over and just get the sum of the forces equals MA. And sometimes in shorthand, they don't even write the sum in front. So a lot of times you'll just see it as F equals MA. But this is the summed forces. It's just not always in every textbook. So why is this helpful? That is a good question. When the force on an object of mass m is due to gravity, so when the only force acting on your object is gravity, well, we know that acceleration would equal gravity, right? So instead of F equals ma, we could write it as F equals mg. Now, that's how we calculate our weight. Our weight, you can calculate anybody's weight if you know their mass and you multiply by gravity on Earth. So if there's a 50 kilogram crate or something sitting on the ground, you know that it's 50 kilograms, but if you multiply by gravity, which is about 10 meters per second squared, that's going to give you a weight of 500 newtons. So this is a usefulness of Newton's second law, is you can actually use it to calculate anyone's weight on any planet. There's not a whole lot on the slide, so there's a smiley face. Now, we talked about how when things fall, they always fall at the same rate. And then we've also talked about how different masses accelerate differently. So this almost sounds like some sort of contradiction. Two things falling, and then they always fall at the same rates, what we said earlier. But then we also talked about, well, if they have different masses, they should have different accelerations because they have different inertias. So let's take a look at that. If we first look at just a brick of mass m falling, well, we can calculate how it falls, right? The only thing acting on it is its weight, its force due to gravity. And we can rearrange this to calculate its acceleration. So this is just the weight divided by m equals gravity, right? I just divided both sides by m to go from here to here. And we see that down here in this equation already provided. The force, that's just the weight. Right? We can change the F to a W to match our notation. So the weight divided by the mass is just G. But look at what happens if we double this. So I need to change my color. So we drop two bricks tied together. So now we have double the mass. So it's true, you can look at the math. We double the mass, but we also double the force, right? There's twice as much crap for the Earth to be pulling down. Instead of just pulling on one brick, the Earth has both bricks is pulling down. So the force due to gravity is also double. Now, just using some algebra, we see that there's a 2 in the numerator, a 2 in the denominator, they cancel. And again, we're left with same thing. So even though they have different masses, they're always going to fall with a rate of gravity, or G. All right, so let's look at 2 examples and then we're going to call it a day. So if we have a 50 kilogram crate, and and we're pushing it with a force of 100 newtons. Okay, it's going to cause, and we're causing an acceleration of 0.5 meters per second squared. Let's determine the force acting on the crate due to kinetic friction. So usually it's a good idea to draw a quick picture. So we have a 50 kilogram crate. We're pushing it with 100 newtons. So we have a push, and then we know it's accelerating at 1/2 meters per second squared, or 0.5, whatever you want to call it. And we also have some kinetic friction that's going to oppose us, right? Always in the direction opposite of motion. But we have no idea what that friction is, so let's solve for it. Okay, well, let's use Newton's second law. So we know that Newton's second law says that acceleration equals the net force, the summed forces, divided by mass, okay? So we're going to call this my positive x direction to the right. Okay, so I know my push is positive. My friction always has to be opposite. So that has to be negative, all right? I've got my forces in there. I don't care about the up and down direction. Yeah, it has weight pulling down. Yeah, it has a normal force going up, but it's not moving up and down, so we don't care. We don't care about those. Okay? We need to take a moment and ask ourselves, are these all the forces we do care about? Yes, those are all the forces. We have the right signs on them, the right positive, the right negative, so we should be good to go. Now, all I'm going to do is I'm going to multiply, let me use a different color. I'm going to multiply this m over, right? Multiply both sides by m, and that's going to give me this statement. Okay, this should be easy, just high school algebra. So I have MA equals the difference in the forces. Now I need to get friction by itself, so I'm going to subtract P to the other side. Okay, and then the last thing I'm going to do, I just need to flip the signs on everything, right? Because I have this negative friction, but I need to solve for positive friction. So that just means I just have to flip all the signs. So I get my positive friction by itself, and that's going to equal the P minus NA. Well, I know my push, I know my mass, and I know my acceleration. So now it's just a plug and chug problem. Put in my values, and it turns out my force due to friction (75 newtons). Okay, now let's look at one more. So if an acceleration if an acceleration terminates during free fall, so something's falling, it's speeding up, and then all of a sudden, if it stops speeding up and starts traveling at the same speed, well, that's its terminal velocity. So let's use Newton's second law to talk about what's going on when something hits its terminal velocity. Because someone jumping out of an airplane with a parachute, they're not going to just like keep falling and speeding up, and then hit the ground at like the speed of sound. Eventually, the force of air resistance is going to cancel out their fall, and they're just going to travel at the same speed. Okay, so we're going to use D for drag, and that's going to be our opposing force here. And it does depend on speed. So that means when we start falling, there's no drag. When we can't fall any faster, maximum drag. So we're going to start with a baby drag at the very beginning. Over time, so a change in time, sometime later, a lot of drag. So drag will increase as we fall. Okay, now, since the acceleration is changing, A will be used instead of G. We're not falling with G, that's constant. That's not happening. Our acceleration is slowly getting smaller. All right, so we're going to define our positive direction as y down. Okay, so we're going to say going down is going to be positive. We can define it however we want to, it doesn't matter. All right, so maybe we're going to jump out of the plane. We've got our positive weight. Okay, that's getting us where we want to go, positive direction. But as we're falling down, drag's going to be opposing us. Drag's going to be pointing up in the negative direction that we've decided. Okay, so we're going to have weight down, drag up. So that's why we have W minus D. And these are all the forces that we're dealing with, right? Just almost free fall, weight down, and then drag up. So the whole idea here is that right when we jump out of the plane, right when we're released from rest for our fall, we don't have any drag yet, right? It's a low speed, it's just started. So drag, we're over here. Drag so small, we're going to ignore it. So in that situation, drag becomes 0. And look what happens. If it's 0, we just ignore it. Right? And we can keep doing this. We know it's just weight divided by mass at this point. And weight we already said was W equals mg. So we can rewrite weight as we move over here. Those m's cancel, and look what we get. We do some algebra to show that right at the beginning of our problem, our acceleration is just g, is the acceleration due to gravity, just like problems from forever ago. But now as we're falling and speeding up, we know that there's going to be more and more drag. So at some point, we know that these things are going to be equal and opposite, which is literally what I have written here. Drag equals the same value as weight, but in the opposite direction. So look at what happens when we do that. So when this happens, we have, let's see, I want to get rid of this middle step. Yeah, so when these are equal and opposite, they're essentially going to cancel each other out. So what's going to go on is this piece here, that's going to become 0. That's going to, they got to cancel each other out. Okay, so that's just going to be no change in newtons, no change in force. Well, a 0 in the numerator just means 0. So look what we have. We have acceleration, 0 meters per second squared. And of course, that's after some time passes. So we literally go from A equals G to A equals 0 over time, right? Some delta T. And that's how you can actually use Newton's law to analyze these situations over time. So we will stop there. And the next time we will talk about Newton's third law.